Hi guys, today we want to finish off lattice energy and also the solubility. Let me show you what we are going to do today, okay? Here you can see this part here, okay? We have already, well, let me just give you the, put red color better. Okay, remember we actually talked about the definition for lattice energy, right? Is a formation. For example, let's lattice energy for sodium chloride. So it's a formation of 1 mole of sodium chloride, which is positive and negative. At standard condition, it's solid here. From is what? Are gaseous ions. Gaseous ions plus Cl minus gas. This is called your lattice energy. Okay, just to review over that. Or sometimes it is written as Le. And it's always negative. See? Always negative. As compared to bond energy, it's always positive. It means how much energy is required to break 1 mole of the covalent bond. Now, the difference between lattice energy and heat of formation is the same, but the products are the same. But the source, the regions are different. The heat of formation is a heat change when 1 mole of the ionic substance is formed from its elements. So it's Na solid plus half Cl2 gas. This is a heat of formation. Okay? So you must know the difference, okay? Now, today we're going to talk about, we have done this already, right? How to solve for this. And here, explain D here in qualitative terms. Let's explain things. The effect of ionic charge, 1, and 2, ionic radius, okay, on the numerical magnitude. It means how the value. This is the value of the lattice energy. Okay, 2 things. One, of course, is the charge of the charge here, charge of the cation. Here is a plus, or M2 plus, or M3 plus, and the charge of the anion, because an ionic substance may have a positive negative charge. Normally, like Cl minus, F minus, Br minus, okay, or O2 minus, or N3 minus. Okay. So all these are the charges. Of course, the ionic radius is how large is this fellow here? Okay, right? Normally, they would say something is same before you compare the other one. But let's look at this first, okay? How does this compare? After that, then we go to solubility, okay? Now, look at the third part here, formation of simple ionic solid. We've done already, isn't it? Right? Where we involve the lattice energy. And now we talk about the formation of simple ionic ions and of its aqueous solution. We're going to talk about this, okay? In terms of this part here afterwards, if we have time, okay? So let's go to the questions on how to explain the difference. See, the difference in numerical magnitude of lattice energy for different substances. Okay, okay, right? The difference. Now let's look at some of the questions here. Page 28. Okay, 28. Here. Right? How would you expect the magnitude? Magnitude means what? The size. Magnitude means the size or the amount, the amount of lattice energy from magnesium oxide compared to that of sodium oxide, Na2O. Of course, in this case, you can see that what is same? The oxide is the same. It's -2, -2. Okay, so the size of the oxide ion, O2 minus, is the same for both. What's difference, of course, is the Mg. Even though Mg and Na are in the same period, right now, okay? So the charge of this is 1 positive. Charge is, well, 2 positive. That's all. And of course, the size, see, not only the charge is smaller here or bigger here, but the radius of this is smaller, isn't it? Smaller radius. Okay. Now you can use the other term called polarizing power. Okay, I'm going to show you now. polarizing power, okay, of cations, okay, is equal to the charge over the radius. Okay, of course the charge here for magnesium is 2, radius is smaller than that, okay, radius here. Of course this will have a larger polarizing power. Okay, so the stronger attraction. So we expect the Lattice energy of this to be bigger than this, which is true. Now let's look at the answer here. I think it's this one here. Okay, let's see here. Okay, right. So magnesium oxide is higher or bigger. Okay, forgot to put the ruler. Okay, see, magnesium, the lattice energy. I want to put smaller. Okay, right, of magnesium oxide, right, is bigger, larger than Na2O. 1 mark. Okay, why? Okay, doubly charged cation. The charge is larger. Magnesium is 2 plus. Whereas sodium is what? Sodium is 1 plus. Okay, right? 1 mark for this. Or bigger what? Charge density or polarizing power. Charge density, same thing we done before, isn't it? Equals to charge over radius. Okay, or smaller cationic, smaller cation radius. Right, because it's go across the period here, sodium here, right? Mg here, right now. This is 2,8, this is 2,8 also there, right? So a more larger proton will attract the 2,8 more, so it's a smaller, this larger radius. Either way you can say. I want to take you back to some theory first, okay? So to explain all this, right? You can see here in the theory, I talk about the perfect ionic compound. Okay, here. So what controls the magnitude? What controls the magnitude? Quantitative controls the magnitude. Okay, we use the words that Cambridge use. Okay, or the amount, size, or the amount, the value. Okay, you need to be very clear of what the words mean. Okay, magnitude means the size, amount. Okay, what does this the value of this depend on? Well, it says it's inversely proportional to the interionic distance. Now this is found in the book. Now normally, well, what does it mean? What does it mean interionic? Let's say there's sodium here, Na plus, and here's your Cl minus. Okay, so it's from nucleus here to the nucleus here. Now this is called your interionic radius. Okay, but normally when you compare two substances, one of them will be same. For example, just now we have magnesium oxide and sodium oxide. That's all. Yep. So what is same? The oxide is the same. So oxide as a magnesium here, 2 plus, and the oxide here. Okay, remember the ions in it. So this and your sodium, of course, sodium Na plus here, and you got 2 of them here. Okay, O2 minus here. Sorry, I have 2 Na lah. Bodoh. Slightly bodoh today. Okay, here, draw. Okay, so 2 Na here. So O2 minus. Okay, now this is called the interionic radius. But normally, if these 2 are the same, put the blue color. Okay, if these are the same, so they just talk about the radius of your cations only. Okay, which is bigger, which is smaller. Okay, all right. Now you can see here in a lot of examples here. Now for the first example here, compared all here, the formulas here. Remember, Na plus, F minus, or plus minus, plus minus, plus minus. Yeah. So the charges are the same. You can see here, there's a formula. There's a formula here. Here. They say lattice energy is proportional to the product of the charges. The positive charge times the negative charge over the interionic radius. This is from the book. Okay? This is how you can actually calculate your lattice energy. Right? Now, let's come to here. So here you get like positive, negative in it, right? Okay? So the charges are the same. So what makes a difference in see, the lattice energy is all different. And as you go down the group of group 7, right? Okay, the LE or lattice energy decreases, become less negative, right? That means the attraction between them is less. Why? Okay, why? You always ask why. Well, because basically here, right, the attraction F is the smallest, and then chlorine, bigger, one charge. No. Bromine, bigger still. Iodine, big lumpy here. Yeah. So the pull of the of the Na plus towards this is stronger now. Okay, so smaller, this smallest, and ionic radius. Okay, therefore stronger the attraction, stronger the ionic bond between them. Okay, strongest attraction. Okay, that would cause you to have a large LE. So why is NaI smallest? Because it's got a very large, what? Large and ionic radius. Okay, or is it I minus? Okay, now then they might ask you, well, for magnesium oxide, this is a bit famous. Okay, it's about 3933, it's about 4,000 now, right? About 4,000. Okay, why is this? Remember, they're always negative, because it's the bond form, isn't it? Exothermic, isn't it? Why is it about 4 times this one here? Right, this is about 1,000. Why this is 4 times? Very simple to explain. Remember, see, right? Now, the charges, MgO, here. See, Mg is 2 plus, O is minus 2. Okay, so you put lattice energy for MgO proportional to 2 with positive times minus 2. Now the interionic radius is about the same. That's what they say. Okay, the interionic radius is about the same. So lattice energy of sodium fluoride is equals to +1 times -1 over R. R will be about the same. So this will be 4 times it. 4 times of this one here. See? Approximately. Okay? So now the other one, of course, is comparing here. Now before you compare this one here, there's a theory called the theory of ions. I want to put this in red. Okay. Okay. The theory of ions assume that ions are perfectly spheres. They're not like polarized, okay, perfectly spheres. That means it's a sphere here, okay, and A plus, and this sphere here. Okay, this is an assumption. Assumption, of course, not really true, okay? So attractive force between this perfect spheres can be calculated. This is called a theoretical value. Okay, so now they did this one here. Okay, so they count here, all right? See, calculated value. This is from theory. That means we assume all these fellows here to be perfect spheres. But is it true or not? Right? If it's true, that means experimentally they should be the same value, because its calculation is theoretical. But here it is more, no? It's 2526 and it's 2326. The difference is about 200. Big difference. Why? How come experimental value don't agree with calculated value? And remember all these fellows here is group 2, right? Magnesium, calcium, strontium, and barium. All this is 2 plus, 1 minus, 2 plus, 1 minus, 2 plus, 1 minus 1. Okay? Right? The charges are the same, right? So Cr minus all here, the anions are all the same. So the difference between down here, of course, is your the radius, right? Like that's why because the radius of this is going down here is increasing, the cation radius, okay, is increasing. Therefore, you expect all this to decrease now. Why? Because the attraction will be less. Now that's one thing, but now why these two don't agree? Right now, but this one agree the most. Right now, see, smallest value here. That means something in here is extra stable, in reality, than this one here. What happens is that magnesium 2 plus here, it's got the smallest ionic radius, so 2 plus here. Okay, right? And barium is a big fellow here. Big fellow here. Now chloride is here. Chloride is here. Now, this fellow here, because now the charge density, call this, okay, or polarizing power. A better word is polarizing power. But the book also says charge density. Charge density, okay, of mg 2 plus equals to charge over the radius, okay, which is equals to 2 over the radius, whatever here. Okay, yeah. Now, of course, in this case here, the charge density of barium is equals to 2 over R. R of barium is bigger than this one here. So this charge density is smaller. Maybe let's say about 2 here. Here is about, let's say, 8. So this fellow here, it means stronger pull, or we call it polarizing power. That means able to pull the electrons. As you pull the electrons, it means that this field no longer become a sphere. They become like distorted. Yeah? Like that. Okay, to form what? Some covalent character. So I say magnesium chloride has got some covalent character. Okay, distorted. Yeah. Okay, that's the reason why. Right? Because of as you go down the group, here, the charge density of the cations will decrease. That means the first fellow here has got both ionic bonds and some covalent character, as you see in A2. Now here, the second table tells you that it all are magnesium. Okay, so the charge density of your magnesium 2 plus here make no difference. But here you can see again the calculated value and the experimental value. Here is the biggest difference. Why? Here is the smallest difference, which means this fellow here is the most ionic. That means the most spherical. Okay? Why is it most spherical? Why this fellow is? That means this fellow here, magnesium iodide has got some covalent character, right? Right? That means it is more stable experimentally. In reality, it's more stable than the calculated value. Which means again, this one has got ionic bonds and covalent bonds. Okay, so nothing is never totally ionic. Nothing is never totally covalent. Now here, all right. So Mg2 plus is here. Here so Mg2 plus, right? But F minus here, because F is a very small ion, and also F is very high in electronegativity. So it will hold the electrons here tightly. So Mg2 plus, even though it's got high polarism, cannot attract it towards itself. That means it remains almost spherical. Almost spherical. Okay? That means it's very ionic in character. That's why difference is 4. But this I minus big lumpy fellow here, right now, is able to be polarized. Right? Yeah. Okay. I minus here. That means we say this to be polarizable. Okay, polarizable. Okay, I minus. I don't know why they cannot work sometimes. We go off it all again, Again, no. Okay. 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 I minus here. Yeah. So the electron density here is spread over here. Okay. So I minus is more polarizable, more polarizable, which means it can form like that. So that means that it's not a spherical shape anymore. So that's why it has got some covalent character. So it's stronger, the bigger it's value here. Okay? But the main thing is this is almost perfect. Almost perfect. Almost perfect ion. Okay now? Okay? So these are some of the things you need to know to answer questions. Okay? Now of course as you go across period 3, you can see like sodium chloride. Okay? Magnesium chloride, aluminum chloride, and silicon tetrachloride. These two are covalent already. Covalent. These two are ionic. Ionic. But this one has got what? Plus some covalent character. Why? Charge density. This Na plus. This Mg2 plus. This Al 3 plus. This Si 4 plus. They all have got 2, 8 on 4 electron configurations. Right now. And of course, this one has got the most number of protons in. So the pull is very strong. See now? That's why they pull all the electrons, the Cl minus here. The Cl minus ion is polarized. See? Polarized, okay? So they pull in to form the covalent bonds. You can see the change there. All because of from here to here, there's an increase in what? In charge density. Charge density of what? Of the cations, the positive charge. Okay, so this is to cover up all the magnitude difference of your what controls your lattice energy. Okay, now the first one here. If you look at here, this page 9, I will come back. See, they say what? See here, explain. I put a blue color. All right, so you can see clearly. Okay, say explain qualitative terms. What are the two terms? Ionic charge, right? Which can control ionic charge. If it's positive, we call it the charge density, or we call it polarizing power. Polarizing power. Okay, right? Because it will depend also on the ionic radius. Same thing here for all these here. We say, well, how polarizable are they? Okay? Polarizable, we call it polarizable. Yeah. If more polarizable, that means you can shift it to change from a perfect sphere to something, like this one here. From perfect sphere to like that. Okay, now, okay? To like going towards forming covalent bond. All right? Okay, now we finished these two here. Now I want part 3. Formation of simple ionic, we are done already. Now formation of simple ionic and its aqueous solution. Now of course for this one we done already, okay? All right, Haber cycle. So now this is part 3 is connected to number 10 here. Interpret qualitatively. Okay? And also quantitatively, no. Okay? Qualitatively means explain in terms of why. The variation, that means the differences. Okay? Varied differences. Differences. In solubility of hydroxides and sulfates of in terms of relative magnitude. This is of course quantitatively. Quantitatively or dative. Okay. This qualitatively means in terms of why. So this is what? The enthalpy change of hydration and corresponding lattice energy for solubility. So what controls solubility? Remember, here is for ionic compounds. Okay. Okay. So we can look at the solubility of ionic compounds. What are the energy terms we're going to use? All right. Now let's look at page 9 here. Okay. I'm going to try to make it a bit faster because we need to go a bit faster. So remember, I've got solution here, right? Solution. What does it mean? Hydration. What does it mean? Of course, we know what it means by lattice energy. Why lattice energy? Because we are talking about what? Ionic compounds. Ionic compounds. Not covalent compounds, huh? Okay. So what are the heat changes when ionic substance dissolves in water? What does it incur? Right? Now, here I have I want to use this one here, okay? Because I didn't have the bit lazy to give you all the data. Actually got from here, but it's easier to use this one here. All right. Now here this says I want to dissolve calcium chloride. Okay, calcium chloride, solid. Okay, so in water. Now water, that means if water here I put aqueous because you don't know how much water is it. That means I want so much water that it will totally dissolve it. Now that is called an infinitely dilute solution. Now it's given here in the marking, see my straight first, okay? See? To form an infinitely dilute solution. Okay, it's very important. But sometimes they just use aqueous solution, which also can. Okay? Dissolve in water to form, and it means you put some more, as you put water inside here, the heat will change, You put some more water, the heat will change, until the point where you put some water, the heat won't change anymore. That means it's called infinite dilution. Okay? It's called infinite dilution. Infinite dilution. Okay? Right? It means no more heat change. The temperature won't go up or go down. Of course, it will go down because it's more water, but it stopped going up. Okay? So now, let's look at this. Okay? So, what does it incur? How does it actually go about the whole thing? Now, we say that when this happened, to go to here, when dissolve, remember this is a 2 plus here. And this is in solid, no. That means among themselves, there's attraction. What attraction is it? Ionic bonds. That means to go to a solution, they must be separated. They must form calcium 2 plus aqueous. See now, totally dissolve, okay? Plus Cl minus 2 of them aqueous as well. Now this for 1 mole. Here 1 mole. 1 mole. How do you know 1 mole? 1 in front 1. Okay? Here 1 mole and 2 moles. So when 1 mole of your substance is totally dissolved, right now this is called the heat of solution. Heat of solution. Okay? Put that thing here. Now let me show you a question that has got all these things. The whole question talks about this whole thing. So I thought it was a pretty good question to explain this. Okay, it is in page 46, 45, the whole thing will be there. 45. All right, say it here. Magnesium chloride. Okay, the dissolving of an ionic compound. They tell you specifically is an ionic compound. Okay, which means it will involve lattice energy. Okay, right? In water, it's accompanied by energy change. Right? So the enthalpy change of solution or heat of solution is called the heat of solution. Okay? Right? Represent by this now. See? Solid is it? Aqueous is it? That means it's infinite dilution until here. Now this is the delta H. They call it SOL only. Okay? Right? They can put this here. Okay? So they say, well, describe in terms of bond breaking and bond making. What happens to the solid ionic lattice? And the ionic compound is on water, 2 marks. Now let me show you here. Of course, it's Mg lah, okay? MgCl2. Okay? It's 2 plus, and that is solid. That means you got magnesium here, Mg, 2 plus, you got Cl minus here, and Mg, 2 plus here, and Cl minus here. So they are all arranged in, of course, Cl minus here, Mg, 2 plus here, Cl minus here. A lattice in. The attraction between them is what? Is ionic. Right. I have to separate them first before they can dissolve it. So to separate them to gas state, no water yet. 2 plus gas to 2 Cl minus gas. What is this? To go backwards here, well, I'm going to put red again now. Okay. To go from here to here is what? Is lattice energy, is it? Because why? The definition for lattice energy is the heat change on 1 mole of the ionic compound, 1 mole of this is for 1 mole, is formed for its gaseous ions in. So this way is called minus lattice energy. Must put the minus in front here. or some book says it's called the reverse lattice energy. You must know when to use it, no? Okay, this further won't work sometimes, I don't know why. I must complain, see, idiot. I think the pen is, the nib is almost gone. Never mind, we tick tock further. Okay, now I can. They must change the nib. Okay, so it's called reverse lattice energy. Okay, which means minus in front. Remember, lattice energy is always negative. So negative and negative is always will give you positive. Correct or not? Here I require energy to break up the bonds. So the first thing, of course, is it is the bond breaking. The first thing, what? I must break the bonds. The bonds are what bonds are broken? The ionic bonds. Ionic bonds between what? Between Mg2 plus and Cl minus are broken. B-R-O-K-N, which is what? Endothermic, isn't it? Right now, because it absorbs it or not. Okay, right now. Now look at the marking scheme. Okay, the first one. Is it the one? No. Okay, ionic bonds. Ionic bonds are broken between what? Mg2 plus. Okay, so I got my thing there. Of course, I say what? Therefore, it is what? Endothermic. It must absorb heat, okay? So the first thing of course, this is to break this down here to form the gaseous is what? Is the reverse, what? Reverse lattice energy, is it? Okay, this is actually, but most time they just say lattice energy, no. Okay? It's actually reverse, minus here. Okay? Now the second thing, what happens to it after this broken up? Now remember, it is here, you plus equals A cubed. So what happens is when they form this one here, now aqueous water has got this is like this. Okay, the covalent bonds is this delta positive, delta negative. Yes. Why is this so? Because oxygen is more electronegative. So when the Cl, okay, let's okay, this Mg2 plus here. When the Cl here, oh sorry, yeah, better put that on better. Okay. Okay, we put this on here. When the magnesium came out as an individual gas, so here, positive here, the water will be attracted towards here, right? Polarizing. So what do you do? So the water molecule surround it. This is a delta negative. Surround like that. Surround the whole thing like a sperm, the sperm and the egg. Okay, surround it. Okay. They form around the whole thing, like the whole sphere. Okay, now if this is very strong, it will attract another layer of water. Okay, so as it attracts more layers, more heat came out, because once the form until it will come out and go away. Okay, that means that the water comes out. That means there's no longer any attraction. Now that is called infinite dilution. Infinite dilution. Okay, now that is what it means by Mg2 plus aqueous. Okay, so here. Now this the heat change when 1 mole of this is changed to Mg2 plus aqueous. Now I'm going to drop this thing here because I want to use a space here. Okay, you can see sorry, I don't know. Never mind. Okay, let's go back here. Okay, so when this form, right, plus AQ, the first, of course, this part here will form Mg2 plus aqueous. Yes, okay. So this one here plus aqueous will go to here. Now this is called the heat of hydration. H, okay. Heat of hydration. Now you will see that here they actually ask you for the next question here. Very tricky, isn't it? Okay, not here. The one before. So I got all the marking scheme ready for you so that you don't have to worry now here. Okay, heat of hydration. Here, okay, right. Let's look at the definition first. Here we are. Okay, right? No, that's not, sorry. Okay, right? Heat of hydration is now. When 1 mole of the ions, okay, or 1 mole of the gaseous ions, right, dissolve in water to form an infinite dilution. It means that like here will be Mg too big, smaller. When 1 mole, remember gaseous, see, 1 mole of ions should be gaseous ions. 1 mole is the first mark. The gaseous is 1 mark. See, this one is 1 mark. So 2 marks mark. When 1 mole of the gaseous ions, right, dissolve in water or solvated or hydrated, dissolve in water completely, you should put that, right? Or dissolve to form an aqueous solution. Either way, this is the best one. Dissolve in aqueous solution to form an infinite dilution. Okay, dissolve plus AQ to form what? To form Mg2 plus aqueous. This means your infinite dilution already. This means aqueous solution. Okay, when 1 mole of ions. Now, what's the difference between this and your heat of solution? Okay, now let's go to here. So this is heat of hydration. Now heat of solution here. See, I ask you, right? What is meant by the heat of solution? So now let's go back to here first. So after the bond is broken here, right? To here, Mg2 plus will attract the water to form this one here. But Cl minus also attract water. Cl minus will be Cl minus here. Of course, it will attract the hydrogen part, isn't it? It's delta negative, delta positive. The hydrogen part. Same thing. Hydrogen here. Okay. Delta positive, and then H. Okay. H. So you will attract the water. Same thing here. And then layer by layer until no more water here. Okay. H. Sorry, H here. Until no more water. That means that means when 1 mole of this is hydrated, when 1 mole of Cl minus attracts all the water to form this kind of dipole bonds, the heat is given up. Always heat of hydration is always exothermic because bonds are formed. So from here to here, I can say, well, this will be here to form plus 2 of them Cl minus aqueous. This is your heat of hydration for what? For chlorine. So 2 times this, okay? Because it's for 1 mole hydration. No, okay? See now, in the heat of hydration. Sorry, here. Okay, 1 mole. Right? It means 1 mole of Cl minus gas, 1 mole of gaseous ion, Cl minus here, plus aqueous to give you 1 mole of Cl minus aqueous. If you have 2, that means times 2, right? If it's, now this is actually delta H already, hydration. If you have 2 here, I will times 2 here, the whole value here. You clear? Okay? Now, which means that which means here, right? To form the whole thing now, this question asks the whole question. After the bonds are broken, right? After the solid things are broken, right? When dissolved in water. So what happens? Number 2, right? The gaseous ions of Mg2 plus and what? Cl minus, what forms what? Forms bonds in. Are surrounded, forms bonds with water. And this is called hydrated with water, right? Hydrated. Okay, to form Mg2 plus aqueous and Cl minus aqueous. Okay, this whole process. Okay, now look at the marking scheme now. See, okay. Bonds, attraction between the ions and waters now. Bonds, forces, intermolecular forces. Okay, you can put intermolecular or dipole attraction. Dipole attractions or intermolecular forces. formed between ions, 1 mark each. Okay, so the whole thing now is called heat of hydration, heat dilution. Oh, sorry, the heat of solution. Okay, so now this is called the heat of solution, Dr. H. Which they ask you now, what is meant by the term enthalpy change of solution now? Okay, so this is, remember now this you look at Hess law. I'm going to put the green color. All right, see Hess law. Hess law says what? Root A to B, a beginning, initial to initially. But this is initial. This is a final. That's not. This is the first root. This is the second root. Okay. So what is the heat of solution equals to? This is the first root. So heat of solution is equals to, first of all, minus lattice energy. It's not. Why not? Okay. Because we're going this way, This way is less energy, right? This way is less energy. So minus, must put a minus, plus what? Plus going forward here. Heat of hydration of what? Mg2 plus 2 times heat of hydration for what? Of Cr minus. See now? This is how you solve the problem. Now, they found that for delta H, right, you know it is, if it is negative or very small positive endothermic, that means this is soluble. That means it will occur. That means that it is, well, the reaction is feasible, they call it. Reaction is feasible. If it's very large, if it's very large positive, that means that it won't dissolve. That means there's no heat of solution. See now. So remember, in this case here, this fellow here is always positive, right? I put blue, very important. Very important. Okay, blue. Right? This is always positive. Why always positive? Because this energy is negative, isn't it? So negative is positive. For this thing to be negative, these two fellows here must be, these two fellows here, these two fellows joined together, this is always negative, this is always negative, isn't it? No. These two fellows joined together must have a negative here, that must overcome the other. Right? No, must be bigger than this. If it's bigger, that means if this is bigger than this one here, right? That means it will be negative, isn't it? That means it's soluble. So the total amount of hydration energy for the cation and the ion must overcome, must be bigger than the lattice energy. They won't say that reverse energy, but they say it must be bigger than the reverse energy. That means it will be exothermic. If it's smaller than your lattice energy here, it will be endothermic. That means it won't dissolve. You clear? Go back and think about it. Now, I'm going to go on. I got only 15 more minutes to try to finish off. Okay. So now, what is the definition for this one here? Okay, here we are. Okay. See, energy change when 1 mole of a substance. For if its hydration is 1 mole of the ions. If its hydration is 1 mole of gaseous ions. Okay, dissolves in water. Dissolves in water to form what? To form an infinite dilution. So here's saying when 1 mole dissolves in water to become equal, or to form an infinite solution. Okay, infinite dilution. Infinite dilution. Everything here is the same. But here is one mole of a substance. That means here include the cations and ions. Here haven't broken up yet. This one requires reverse lattice energy. Here it's already broken up. See now? See? So the difference in this is heat of solution. Okay? Now let's look at the whole change. Okay. Now here's the whole. They ask you now to calculate. All right. Use the following data to calculate the enthalpy change of hydration of the correct ions. you may construct the energy cycle. Okay, so you want to do the cycle, you can also do the level you want to lah. So you must know the whole change now here. All right. So always start. So how do you start the whole stupid thing? You always start with the heat of solution. Okay. You may not know the value, but it's okay. So Mg Cl2 solid. Right now, here the solution is 1 mole of the compound, isn't it? Plus AQ. It means this will be an infinite dilution to go to, right? Dissolve in water to form what? An infinite dilution, which means what? Mg, what? 2 plus what? Equals plus what? 2 Cl minus equals. Now this is called your heat of solution. Is it given or not? Huh? Of course. Right? This is the one here. Now, what's the process it undergoes? That's why this question is very good. It tells you everything here. First of all, this must change. The bonds must broken in. The what bonds? Ionic bonds must break to give you what? To give you the Mg2 plus. Gas plus what? 2 moles of Cl minus gas. And what's this called? Reverse from here to here is lattice energy. So the reverse is called minus lattice energy. Okay? Right now, which is actually minus what value? Minus what's the lattice energy here? Here. Minus 2524. That means you add together, you times it, it's positive. That's why you require energy. Now here, to go from here to here, what is this? This is your heat of what? Hydration. Or what? Of Mg2 plus. Okay? Right? Given on? Yes. Equals to minus 1925. Notice it's negative, isn't it? Why? Because bonds are formed, isn't it? Between water and Mg2 plus. Here to here. People make the mistake here because of one thing I say, okay, now here to here is your heat of hydration. Okay, remember hydration of Cl minus 1. Okay? Right. Let's say we don't know X. That's all. But here, see, for this one is for 1 mole of Cl minus. Here how many moles? 2 moles. So it's actually 2 times it. But you ask for only 1 mole. Okay? Right? So Hess law. I put a red color now. Hess law. Okay. So this is, remember, initial state. This is your final state. Yeah. So heat change for system A, system 1 to by root 1 and root 2 is the same, is it? So I put down here delta H of, I don't know why. Okay, never mind. I want red better. Very stubborn. Okay, wait. See, it won't come out. Spaghetti. Come on. Won't come out. I think I must change the nib already. Okay. Delta H of solution equals to, remember, minus LE. Must put, remember, it's going this way now. Yeah. And plus heat of hydration for what? Mg2 plus. Plus, remember, 2 times delta H hydration for Cl minus Cl. Okay, what is this one here? 1 minus, put a sign up, put a sign, okay. Minus, what is this? Put a sign. What is this? Minus, minus it. 2524. Plus, what is this here? Put a sign, put a sign. What is this? Gundu? Okay, minus. Yeah, wrong lah. I say, I'm so blind. Try to hurry lah, I tell you. Idiot. Okay, I hope can, Come on. Come on, baby. Okay, solution is this one here. Sorry. Solution is 155. Okay? LE is correct. Okay. So here hydration is what? This one is it? I don't know. Minus, okay? Why? Because bonds are formed, is it? Minus 1925. Yeah. plus 2, let's say x. Okay? So here's minus 155. Here is equals to, let's quickly go about it. Time is almost up, man. Never mind. Okay, I should have done this earlier. 2524. Okay, it's plus, okay, now here's minus 1925 equals to, this will be this will be plus 599 plus 2x. So 2x is equals to minus 155, brings over is minus 199. Okay, it's equals to plus here 155 equals to, okay, it's equals to minus 754. It's 2x. What's x equals to? Divided by 2, isn't it? So it's minus is 377. Okay, let's put the answer. Should be don't forget kilojoules per mole of iron. Okay, this one. Okay, see, minus, perfect answer, minus 377. Okay, right? See now, so this whole thing, right? Talk about a heat of solution. Now let's look at the cannot. Okay, now I think I'll stop here. Or I'll go on a bit more. Okay, but I want you to look at what they say here. Can I? All right, this question is very good because it asks you for definition of heat of solution. Asks you for the earlier, of course, it's not here. It's the earlier question here. They ask you for the heat of what? The heat of hydration. Okay. Now I want to go through. I will change this. I will come back this later. Next time. I want to talk about now how the question come out for the lattice energy. Okay. To compare different types of compounds. Okay, let's look at the first one. Actually, that's earlier, but I was too excited to do this one here. 28. Now, okay, right? How would you expect the magnitudes of lattice energy of magnesium oxide to compare with that of sodium oxide? That's 2 marks each. So, I ask you for magnitude of lattice energy. So now it's on lattice energy. Okay. Now, magnesium oxide is MgO, yes, yeah. I put down here so it's easy for me. Okay, sodium oxide is on here. So, which is bigger? Magnitude, which is bigger? Right now, look here. Oxygen oxide here is same. Okay, Na is Na plus, Mg is 2 plus. Now, remember, Na and Mg are the same period, isn't it? Okay, so of course, the charge is 2 positive. The more stronger attraction, isn't it? Right? And also, this one is a small Mg2 plus a smaller radius. Okay, right? So the answer you can find the same here. See, okay. Yeah, I thought about this result. I felt I thought about this already. Okay, but Mg is more larger than this one. I think I talked about this already. Okay, right? So 1 mark for larger, 1 mark for doubly charged Mg2 plus, okay, or smaller cations. Second question. Okay, 29. Right, here I didn't do it. Suggest with explanation for each case how the lattice energy of magnesium, right, compared to that. Okay, now here's magnesium chloride, Mg, Cl2. This is chloride. Okay, so which is bigger? Compare the magnitude. Explain, compare that. Right? Which is bigger? Of course, it's one. Yeah. Why? Because Cl same. Right. The charge is again 2 positive. Is only 1 positive. You know. Also, the radius is smaller radius. Right. So Mg2 plus is greater in lattice energy than NaCl. Why? Because Mg2 plus is plus 2 charge, okay? Or you can say Mg2 plus is the what? Smaller ionic radius, right? Okay? Now, Mg2 plus and MgCl2 with calcium chloride. The thing is, both are in group 2, isn't it? Plus 2. So you cannot talk about the charge anymore. That's all. You must talk now about the radius. And magnesium is up here. Okay, calcium down here. In group 2. So calcium 2 plus is what? Is bigger size now. Okay? Bigger radius. So it's inversely proportional to radius. Right now, bigger radius means that lesser polarizing power. So of course, this will be lesser. So magnesium chloride is still greater than the Le than calcium. All right. Why? Because Mg2 plus has got smaller what? The same idea here. Cationic radius. Okay, or larger what? Polarizing power. Okay, look at the marking scheme here. Right, see? Okay, Le for this one here, I'm going to put the, come on. Okay, see now, larger, is it? Greater than sun. Why? Mg2 plus higher charge. So then, okay, or smaller radius. Either one, dash means either one mark each. Magnesium chloride is greater than calcium. Why? Mg2 smaller. You put smaller cationic radius, better. No, you're my student, is it? So don't be idiotic. Now here, now let's look at this calculation, okay? We do one more calculation here. Okay, F. Yeah, not here. See the energy here? All right. Okay. Let's do one calculation, okay, for this hydration stuff. Is there one? Okay, one more, and then we're in hydration. Now here is I don't do something. Okay. This one we do later, okay? Right? Wait, let me look here. Solution. 42. Okay. Look here. Use the following data to calculate the lattice energy of calcium nitrate. You may find but it's helpful to construct the energy. Of course, here, right, it talks about what? See, solution. So we ask you to find this calcium nitrate lattice energy, which means what? What's the equation for lattice energy? 1 mole of your this one here, right? Formed from what? Gaseous ions. Plus 2 nitrate here, gas. So how do you start? You start with the heat of solution. Remember, because it's all solution. Okay? So now you write the equation first. So heat of solution means that 1 mole of your substance in it. Not this one here. This is your lattice. This is your lattice energy, right? This is your Le or delta H what? LATT. Okay now. Okay. We start with heat of solution. Which one? Calcium nitrate to solid plus what? Equals to form what? Infinite dilution. Ca2 plus equals plus 2 moles of NO3 minus 8%. Yeah. So this is our heat of delta H of solution SOL equals to, given here, minus 19. Okay, so what must do first? You must break this up, is it? The bonds between the 2 plus. Now this is ionic, of course. You better know, you don't know, you die. Okay. So to go to your ions, Ca2 plus gas plus 2 moles of NO3 minus gas. What is this? Of course, the reverse of this is it. No, which means minus what? Lattice energy, is it? Yes or not? Yep. Now bring the equals down here, plus equals, of course, from here to here is a what? heat of hydration of calcium 2 plus. From here to here is a heat is 2 times 2 times heat of hydration for what? Of NO3 minus. Okay, use Hess law, right? So Hess law says, let's do the blue color. Blue color, come on, blue color. Okay. Okay. Now this, of course, is a reagent here. Okay, initial. This is your final. Root 1 here. Okay, so heat of solution, which is minus 19, is equals to what? Minus lattice energy plus what? What is it? Heat of hydration. Well, sorry, H of hydration for NCA2 plus what? 2 times, I tell you, forget, knock your bloody head, I tell you. HY of what? NO3 minus. Okay, substitute inside. Yes, not. Okay, now remember, you're given here, heat of hydration for this is how much? This is given to, see here, okay, minus 1650. 2 times, now this for 1. You always remember, this for per mole. So it's 2 times minus 314. No, don't be an idiot. Okay, so minus 19 equals to minus LE. Very important, put the minus sign there. Okay, plus what? Plus minus 1650 plus 2 times minus 314. Okay, now let's look at the marking scheme. Okay, to make it easy for us. 15 November 41. Okay, quickly. November 41. 15 November 41. I didn't do this. I'm sorry about this. Remember, marking scheme. 15 November 41. Okay, 15 November 41. Quickly. 15 November 41. Down here. Okay, here ready? 41. Okay, this will be faster for us. Okay. The next one we'll do the group 2 ideas of solubility. Okay. So here you can see smaller. All right. See now. Okay. See now. Okay. So here you bring this over here. It will be what? Lattice energy. Put that thing here. So it should be lattice energy equals to, bring 19 over, 19 minus 1650 plus 2 times minus 314. Okay, now let's say, did we get that now? Okay, so you put, remember, it's not here, right? You bring this over, not because minus, you bring over, it'll be what? Lattice energy equals to 19, minus 1650, right? Times 8, so it's minus 2 times 314. Right or not? No. Okay, 19 is not plus, it's not. This is equals to 19 minus 165. You can solve it out, minus 2 times 314. Solve it out. The answer is this. Cannot. Okay, now let's look at the last part here. Okay, let me finish off. The standard enthalpy change of hydration for Ba2 plus is this one here. Okay, Ba2 plus is here. Okay, heat of hydration. That means Ba2 plus gas plus aqueous to give you Ba2 plus aqueous. Okay, right now. Okay, that means water surrounds it. So just explain why heat of hydration is less exothermic than heat of hydration for calcium. Calcium 2 plus gas. Again, man. Idiot. Okay, gas, I must change the name already, plus AQ is equals to calcium 2 plus aqueous. Now this is the heat of hydration for barium 2 plus. This is the heat of hydration for calcium. They say why is one less? It means that this one, right? Now this one is bigger. It means the minus 155. Okay, bigger now. Okay, why this is less exothermic? It means it's more. Why? because of the size, the same charge, same charge, right? Ba2 is the bigger, it's big down the group, it's big size. The ionic radius is bigger, but it's smaller. So because, okay, firstly, they have the same, both calcium 2 plus and Ba2 plus, same charge, right now. But 2, calcium 2 plus, the size smaller than Bm2 plus, smaller. What happens? Therefore, who has got more polarizing power, more charge density? Of course, calcium. So calcium 2 plus has higher what? Charge density, or what? Or polarizing power, polarizing power. To attract what? To attract water, to attract more water. Forming more bonds, more bonds, therefore give out more heat. Okay, now let's look at the marking sheet. See? Okay, Ca2 plus smaller, okay, or has larger charge density. Okay, 1 mark. Attraction more water, yeah, see, the second mark. Ca2 plus, they are high charge density, but stronger attraction. Okay, for the bond. That means stronger bonds. So it's on here. The 2 marks here. Okay? All right, I finished now. All right. Okay, goodbye. Okay. Stop.